Section: Introduction. In this section, we discuss language models trained on predicting the next token, which show impressive reasoning, logical, and efficient fine-tuning abilities. When neural networks reach a global minimum of training loss at the end of training, it is known as the interpolation regime. The key question here is whether these models will perform well on the test set. While these models generalize statistically due to training on large datasets, this does not guarantee good performance on specific tasks. We suggest studying these models in the saturation regime instead, where models reach a global minimum of test loss during training. Since the minimal test loss may not differentiate between good and bad model performance, we need to explore additional properties of the minimum found by our algorithms. To do this, we should move away from the average risk concept in statistical learning theory and focus on more specific goals like rule extrapolation or data efficiency of fine-tuning. The non-uniqueness of the minimum test loss can be understood through identifiability, especially in probabilistic models. Different models may look the same in terms of likelihood, making them non-identifiable unless they cover the entire sequence space. While this concept is well studied in statistical inference and causal discovery, we aim to highlight its practical implications for language models. Our contributions include pointing out the limitations of statistical generalization in understanding language models in the saturation regime, demonstrating our stance through 3 case studies, outlining key topics for study in this regime, and suggesting future research directions. Statistical generalization assesses how well a model's performance on training data extends to unseen test data drawn from the same distribution. Traditional statistical learning theory attempts to limit the generalization gap based on the complexity of the model class but struggles to explain the success of deep learning. Approaches like PAC-Bayes, information theoretic bounds, and algorithmic stability provide more relevant bounds based on the learning algorithm or the learned hypothesis. The appeal of statistical generalization lies in its universal applicability across domains without needing domain-specific knowledge. While understanding good generalization requires some domain-specific insight, the interpolation regime, where models can perfectly fit training data, has shifted focus to training dynamics and inductive biases for statistical generalization. We argue for a shift beyond the interpolation regime to study language models in the saturation regime to uncover the inductive biases behind good generalization. Identifiability is crucial for statistical models, determining if a model can be uniquely recovered from observed data. In machine learning, identifiability ensures a unique minimizer for the test loss, allowing us to reason about properties of this optimal model, such as good extrapolation or intervention effects. Section Summary. In this section, we delve into the importance of studying large language models, LLMs, in the saturation regime to understand their generalization capabilities beyond statistical measures. We highlight the limitations of statistical generalization and emphasize the need to explore the properties of the minimum test loss found during training in LLMs. By focusing on the concept of identifiability in probabilistic models, we aim to uncover the practical implications of non-identifiability for LLMs and propose potential research directions to enhance our understanding of these models. Section: Identifiability in less than AR greater than less than LLM greater than. In this section, we discuss the identifiability of probabilistic models. By an probabilistic model, we mean a collection of conditional distributions that also define a collection of joint distributions over sequences. These conditional distributions usually share a set of parameters. We outline 3 important notions of non-identifiability: functional non-identifiability, epsilon non-identifiability, and parameter non-identifiability. Functional non-identifiability occurs when the collection of conditionals is not uniquely determined by the joint distributions they define. Epsilon non-identifiability relaxes this notion and suggests that there are properties of models that close models do not possess. Parameter non-identifiability means that functionally equivalent models can be described by different sets of parameters. Probabilistic models are inherently non-identifiable, meaning multiple models with perfect generalization may exist. We showcase what this means for language models through 3 case studies matching the 3 notions of non-identifiability. In the first case study, we consider training a language model to fit sequences from a probabilistic context-free grammar where the number of A-S matches the number of B-S. We introduce the concept of OOD prompts, which are prefixes with 0 probability under the grammar. We show that the completion distribution for these prompts is non-identifiable, meaning properties of the model dependent on these completions are also non-identifiable. Rule extrapolation, where the model respects certain rules when completing OOD prompts, is attributed to inductive biases. We conduct an empirical demonstration using a transformer model trained on the grammar and evaluate its zero-shot rule extrapolation performance. The model shows the ability to extrapolate the rule in a significant proportion of cases, even though the loss function does not explicitly consider this. Training additional models with adversarial or oracle settings further confirms that rule extrapolation performance can vary widely despite achieving minimal test loss. This highlights that probabilistic language models extrapolate rules in meaningful ways due to additional inductive biases. Section Summary. In this section, we delve into the identifiability of probabilistic models, specifically focusing on 3 key notions: functional non-identifiability, epsilon non-identifiability, and parameter non-identifiability. Functional non-identifiability arises when conditional distributions are not uniquely determined by joint distributions. Epsilon non-identifiability introduces the concept of near minima in models, and parameter non-identifiability highlights how equivalent models can be described by different parameter sets, impacting transfer learning and fine-tuning. These non-identifiabilities are crucial to understand in probabilistic models, as they can lead to multiple models with perfect generalization behaving differently, as demonstrated through case studies in language models. Section. In this section, we explored the concept of non-identifiability and its implications. We began by considering scenarios where certain sequences have very low probabilities under the pre-training distribution. In such cases, models may appear equivalent based on test performance but can behave differently on rare sequences. This phenomenon, called epsilon non-identifiability, relaxes the traditional definition of identifiability by allowing for a small difference in performance metrics like the Kullback-Leibler divergence. An example of epsilon non-identifiability is illustrated in the context of in-context learning, ICL, where models are evaluated based on their ability to perform downstream tasks without fine-tuning. Various theories demonstrate the emergence of ICL in simplified settings, such as transformer models trained on regression data. However, we showed that in real-world scenarios, deviations from these assumptions can lead to epsilon non-identifiability of ICL. Furthermore, we discussed how the emergence of ICL is not solely dependent on minimizing negative log likelihood. Even if a language model fits the pre-training distribution closely in terms of Kullback-Leibler divergence, it may not exhibit ICL. Our analysis revealed that for a mixture of hidden Markov models, HMMs, in pre-training, the language model becomes an in-context learner as the number of examples in the prompt increases. In summary, our findings highlight the complexities of identifying and achieving in-context learning in practical machine learning scenarios, emphasizing the need to consider nuances beyond traditional model evaluation metrics. Section Summary. In this section, we explore the concept of non-identifiability and its implications on in-context learning, ICL. We investigate scenarios where models may appear equivalent based on test performance but behave differently on low-probability sequences, termed as epsilon non-identifiability. This challenges traditional notions of identifiability by relaxing the requirement for exact equivalence and emphasizes the importance of model performance over minimizing loss, especially in generative models like transformers. Section. Case Study. Parameter non-identifiability and fine-tuning. In this section, we delve into the case study on parameter non-identifiability and fine-tuning. The way we set up the parameters of a neural network impacts how it learns. This leads to parameter non-identifiability, FIG, Case_study_3, where models that are functionally the same can behave differently when fine-tuned and transferred to new tasks. This non-identifiability is crucial in large language models, LLMs, because they are often fine-tuned on new datasets to tackle specific tasks. For instance, when given the same pre-training loss, a narrow and deep transformer may perform better after fine-tuning than a wide and shallow one. To illustrate parameter non-identifiability, a study embedded a small transformer into a larger one while keeping them functionally equivalent. They found that despite having the same pre-training loss, the optimization process favored the larger model with flatter minima, resulting in a 10% difference in downstream accuracy after fine-tuning. This example underscores the importance of understanding which parameter setups are beneficial for enhancing fine-tuning and transfer in LLMs. A popular method for fine-tuning LLMs is RLHF, which recent findings suggest may succeed on out-of-distribution (OOD) data due to a specific bias. Another study showed that RLHF outperformed supervised fine-tuning on OOD data but at the expense of generating less diverse completions. The authors argued that RLHF has an inductive bias that pushes the LLM to optimize for OOD data. We need to shift our focus to studying how different parametrizations influence gradient dynamics. Cref. Fig. Case_study_3. We propose exploring a regime called the saturation regime, where our model achieves near-zero training and testing losses. This regime is crucial for understanding phenomena like zero-shot OOD extrapolation and few-shot learning. By studying this saturation regime, we can uncover inductive biases that lead to beneficial model qualities not explained by traditional statistical generalization. To advance research in this direction, we suggest investigating new identifiability metrics that capture desired properties like generalization and transferability. We also advocate for studying inductive biases that shape model behavior in weight or function space, enabling us to predict OOD performance and transferability regardless of loss values. Additionally, we propose extending identifiability theory beyond the assumption of independent and identically distributed (IID) data to better understand LLMs. In conclusion, our exploration of parameter non-identifiability and fine-tuning sheds light on the intricate dynamics of LLMs and underscores the importance of studying inductive biases and identifiability metrics to enhance model performance in various tasks. Section Summary. In this section, we explore the concept of parameter non-identifiability and its impact on fine-tuning in large pre-trained language models, LLMs. The study demonstrates that functionally equivalent models can behave differently during fine-tuning, leading to variations in downstream accuracy. Understanding the optimal parametrizations for improving fine-tuning and transfer in LLMs is crucial, especially considering the inductive biases that influence their success on out-of-distribution data. Section. Discussion. Where next? In this section, we will discuss our main message, which emphasizes the importance of studying large language models, LLMs, in the saturation regime to achieve perfect generalization. However, achieving statistical generalization does not guarantee the practical model properties we are looking for, such as out-of-distribution, OOD, generalization and transferability. These properties are linked to qualitative, non-problem-specific inductive biases. We will outline promising research directions for studying LLMs in the saturation regime, focusing on generalization measures, computational language modeling, and inductive biases. When it comes to generalization measures, while statistical generalization provides a solid framework, it alone does not explain crucial properties of LLMs. We will discuss alternative generalization metrics that better match the characteristics of natural languages and suggest adapting statistical generalization tools to formalize these metrics in the saturation regime. We will delve into compositional generalization, which refers to a model's ability to understand combined features by grasping individual features. This capability enables models to perform well on OOD data. We will also touch upon systematic generalization, which involves composing rules rather than syntactical compositions. This type of generalization is crucial for reasoning tasks. Additionally, we will explore symbolic generalization, which involves transferring learned responses from training data to symbolically related situations. This concept is particularly relevant for using LLMs to solve complex mathematical problems. In terms of computational language modeling for studying transferability, we will advocate for using formal languages as a testbed and developing computational models for LLMs. Formal languages, such as probabilistic context-free grammars, PCFGs, can serve as excellent tools to study compositionality in LLMs. We will also discuss how computational models of languages can offer insights into understanding LLMs, such as modeling regular languages as finite state machines, FSMs, and the computational model of PCFGs. Furthermore, we will explore how a new programming language, RASP, can describe a computational model for transformers, shedding light on architectural inductive biases in LLMs. By leveraging computational models of LLMs and algorithmic information theory, we can better characterize the inductive biases present in these models. Section Summary. In this section, we emphasize the importance of studying language models, LLMs, in the saturation regime to achieve perfect statistical generalization, but note that this alone does not ensure practical model properties like out-of-distribution, OOD, generalization, and transferability. We propose exploring research directions focusing on generalization measures, computational language modeling, and inductive biases to better understand LLMs in the saturation regime and improve their performance on diverse data types. By investigating compositional, systematic, and symbolic generalization, as well as leveraging computational linguistics and formal languages like probabilistic context-free grammars, PCFGs, we aim to enhance our understanding of LLMs and their ability to generalize and transfer knowledge effectively. Section: Inductive biases for understanding less than LLM greater than. In this section, we discuss the importance of exploring inductive biases for understanding LLMs. Instead of focusing solely on inductive biases for statistical generalization, we suggest studying broader inductive biases that are not specific to particular problems or losses. These qualitative characteristics are valuable even in the saturation regime, as they help us analyze performance on new tasks and different generalization measures. We encourage research that combines statistical generalization with these LLM-relevant inductive biases, such as examining extrapolation performance in relation to statistical generalization ability and the presence of an inductive bias. To illustrate the necessity of LLM-relevant inductive biases, we present examples of qualitative properties relevant to specific DNN models and tasks. For instance, sparsity, often enforced through explicit regularization in machine learning, can also emerge from inductive biases alone. In certain cases, gradient descent on linear diagonal networks leads to sparse solutions, while deep matrix factorization tends to produce low-rank solutions. Additionally, for models satisfying certain assumptions, gradient descent can solve kernel ridge regression with L1 regularization. Neural networks implementing Boolean functions exhibit simple parameter-to-function mappings in terms of Lempel-Ziv complexity and tend to converge towards low-entropy functions. Furthermore, insights from algorithmic information theory, such as Kolmogorov complexity, offer valuable perspectives. Connecting model properties to the Kolmogorov complexity of generated text in LLMs could indicate a preference for low complexity, potentially improving compositional generalization. Despite the incomputability of Kolmogorov complexity, these insights remain relevant for understanding LLMs and constructing versatile models. Real-world data and even randomly initialized neural networks exhibit a bias towards low complexity, influencing the learning process and generalization capabilities. Moreover, the transformer architecture plays a crucial role in shaping inductive biases in LLMs. Viewing RASP as a computational model for transformers provides a framework for characterizing the algorithms LLMs can execute efficiently and compactly. Mechanistic interpretability, aiming to uncover the internal mechanisms of a model, is another avenue for identifying inductive biases based on the transformer architecture.